So where we're at now should be kind of chapter 16 here. And in chapter 16 was sort of the back end of that hill of kind of the conceptual information. And in this chapter, we have things like KSP. Remember that KSP is really the solubility product, and it really is sort of the equilibrium for insoluble, spell that right there, soluble salts. So all these had a very similar sort of arrangement in terms of how the equation is written. We always had our solids here for the most part on our reactant side. We had our aqueous ions on our product side, which gave the KSP a little bit different than a lot of the equilibrium sort of constants. It pretty much was just products. We obviously do it the same way as any other equilibrium. We use the coefficients as those exponents and stuff like that. Because these are typically the equilibrium constant for things that are typically solid, that means in most cases the equilibrium did lie over here towards the reactant side, which, as we saw, KSP values were typically very small values. So these guys were, again, very small sort of values. We sort of work these problems. There's sort of two sort of KSP type problems that we come across. One is a problem where they just give you the KSP value, and we do sort of an ICE table. One sort of difference in sort of the ICE tables that we typically do with KSP is that we, for the most part, use a different letter. It doesn't really matter in terms of the letter, but we sort of assume 0, 0, and then plus S, S, and S. And obviously those guys would go into our KSP expression. Remember that when we use S here, it does stand for the molar solubility, which is, again, I guess a fancy way of saying molarity, basically. So basically we're figuring out the molarity here. We could also talk about the solubility in grams per liter, which was another very common sort of unit that was there. So, if you're given just a KSP value and nothing else, like, hey, what is the solubility of silver chloride in water? This is sort of how you would set it up. Obviously, you would go into the KSP expression. You would solve for S. And again, S would give you that molar solubility. That would be, again, basically the molarity. We also saw there, a couple of things that can kind of affect sort of the solubility in sort of KSP. One major one was common ion, just like sort of with acids and bases. Common ion, again, being present would indicate that it would be present, obviously, on the product side, and that would shift the equilibrium to the right, and it basically would decrease the solubility of a salt. In terms of the ICE table, the importance of that is, one of these guys would have a starting number, not necessarily be 0, and you would incorporate that into your calculation. We also saw things like pH can play a role in solubility as well. Again, especially a pH or an equilibrium that involves something that has hydroxide in it, maybe some H plus or H3O plus. These guys could very much be sort of affected, the solubility by pH. Insoluble acids are soluble in bases, and vice versa. Insoluble bases are soluble in acids. And again, we saw this, for example, I think maybe we looked at magnesium hydroxide or something like that, which obviously is a base in this case. And the idea behind that is, you could go through your sort of KSP problem here. You could actually figure out what is the concentration of hydroxide at equilibrium. And you could kind of get like a baseline pH of where that solution would be at under sort of normal conditions. And then obviously, if you sort of increase the pH, it would be like adding more hydroxide, and that would cause the equilibrium to shift to the left and become more insoluble, less soluble. If you lowered the pH, that means you would be adding more H plus to that. So if you happen to kind of lower that pH in this case, that means you have more H plus, and OH minus are going to come together to make water, and that would essentially remove hydroxide from this equilibrium, and it would become more soluble. So again, that's what's meant by that. When we add the acid really to this base solution, we're removing that hydroxide because there's much more H plus in that solution, making water, causing the equilibrium to shift to the right, causing more of that solid really to dissolve. So these number of things really are important in terms of, whether or not perhaps you will see a solid form, not see a solid form, affects sort of the solubility of a salt. Another major one is that we talked about in terms of sort of solubility of salts is concentration. And, just because solubility rules, as we talked about, tell you that when you basically mix these two things, you should get a solid. Concentration is really important in terms of whether or not you will sort of see that solid form. That's where we were able to really bring about another sort of calculation that we've seen previously, which was Q. Again, we could look at Q, which is our reaction quotient, and then we're again calculated basically the same way as you would calculate K. And we can compare Q to the KSP. And if Q is less than the KSP, we would expect no precipitate formed. And it basically would be sort of an unsaturated solution. If we calculate Q and it does equal KSP, it would be pretty much a saturated solution. And a saturated solution is pretty much, that exact point where all of the solute would dissolve in a solution. So, you're at that tipping point right there of you'll probably start to see some solid form, but you're at that point where you're pretty much at the maximum amount that you could kind of keep sort of dissolved in the solution. And past that point, if we calculate Q and is greater than the KSP, again, we would expect a precipitate to form, and that would be a supersaturated solution. And that's pretty much when you get to that sort of saturated point where that's kind of the maximum that will dissolve. It's that tipping point where you then just kind of go over, and pretty much that solute that's in that solution basically cannot remain. So it does have to sort of form a precipitate. So again, if you have sort of the wrong sort of concentration of these ions, you may not see that solid form. In relation to this, we talked about sort of selective precipitation, where you can basically figure out things like, what is the concentration that's needed to precipitate out a ion from solution. So I think we looked at in lecture an example where we had, I think, bromide and chloride in there, and we wanted to add some silver. And using our KSP values, we could really kind of hone in on what the correct concentration of silver that would be needed, for example, to precipitate out the bromide. And again, you could just use the KSP expression to do that, as long as you know, say, the concentration of the bromide that's in that solution. So we knew the concentration, we can find the KSP value. We basically can rearrange this guy. And whatever we solve for here in terms of the silver concentration, again, represented basically the minimum amount of silver that's required to start to see bromide sort of precipitating out. We could also, in this example, like we talked about in the lecture, have done it for chloride like we did as well. And we would know sort of the minimum amount needed for chloride to precipitate out. And then we could kind of really keep the range between those two, and we could get out all the bromide, and then perhaps we would get out all the chloride. Remember that we could also use KSP values to compare which one we would think would be more soluble, but there was a sort of exception on that, or sort of a note to that, that you can only use the KSP values if the two things you're comparing, or maybe three things, or however many things, that they do break apart into the same number of ions. So for example, if we were looked at the KSP values for silver chloride, breaks apart into silver and chloride, and silver bromide breaks apart obviously into silver and bromide. They both basically break apart into two ions, which means we can use the KSP values from the table to determine which one should be more soluble. The larger the KSP value, the more soluble it is. Again, the larger the KSP value would mean we would have more products, and more products means aqueous ions. Obviously, if we threw into the mix here, actually here we'll just do the one we just did there, magnesium hydroxide. That gives us magnesium plus a couple of hydroxides. That is 3 ions, which means we cannot use the KSP values to compare that to the other 2, because it breaks apart into a different number of ions. In a situation like that, you actually have to do the calculation like we talked about to figure out what is the molar solubility, for example, of each of those things, and then compare it that way. But again, if it's sort of an apples to apples sort of comparison, same number of ions in each of those, you can definitely compare them. Any questions on that there? Okay, and lastly, sort of the last part of this chapter that we came back to just recently was about complex ions and KF. And that also was slightly different than some of the other things that we did with equilibrium. So our KF, which is basically our complex ion equilibrium, unlike sort of KSP, KF is actually the opposite situation. These values are typically very large, which means, when we put something together, like say silver plus, we'll do a couple of ammonias, and we set up an equilibrium that makes this complex ion, such as this, because these values are so large, it really does favor this sort of reaction almost becoming like a one-way reaction heading towards the products, because there's such large values there for that KF. And what that means is typically when we do our ICE table here, there's 2 assumptions, let's put that out, 2 assumptions that we typically make because of the large value of the KF here. We assume that the metal, whatever the metal may be, the metal is going to be used up completely. And what that means is when we actually do this, we would just want the molarity of everybody here. Get rid of that arrow, maybe. So we'd want the molarity of everybody, of the metal, of the ligand, and 0. And the change part here would be always the metal here, the molarity of the metal. This obviously would be 2 times the molarity of the metal. And this would be plus the molarity of the metal. And what that typically will do is 0 out your metal. Obviously, will give you a number here, give you a number here for the other guys. But the one thing that we talked about was, even though it's pretty much always like almost 100% heading to the product side, and that the free metal ion really should be used up, it is still an equilibrium. And that means that, some of it is going to kind of edge itself sort of back the other way, a very small amount. And what we could do is, although we zero it out, we then could go back and sort of solve for it using our KF expression here. And at this point, what you would know from this first sort of ICE table that you did is you pretty much will know everybody's concentration at equilibrium, except for the metal, which in my case would be the silver. We would know this guy's, and this value. Rearranging would solve for what the free silver concentration would be in that solution. And the second part of that assumption is this number that we get, the free metal ion, when you do calculate it, should be a very small number. And if you remember a lot of the examples that we did, the metal came out to something like times 10 to the minus 13 or times 10 to the minus 16, almost pretty much not there. It's a super small number. And that does sort of validate our assumption. If you did this and you ended up with a free metal concentration that was very, very large, probably something is wrong. And the reason for that, again, all really boils back down to the value of the KF, because of that really large value of KF. And as we talked about, pretty much when there's a good ligand, for example, like NH3 that's around, it's going to want to form this complex ion. And as we talked about, that's essentially, what happens in that group one qualitative analysis, as we talked about. We form silver chloride, and just by adding the ammonia, the presence of that ammonia near a silver, they want to come together so badly because of that very large K value that it actually will make the solid right go away. And then you can bring it back, and it will actually form the complex ion, overstaying in the sort of solid. And I think if I remember correctly, we did a calculation somewhere in this chapter, I think, and we did that sort of calculation about what is the solubility of, silver with ammonia being present. And I believe, if I'm not mistaken, in terms of silver chloride and ammonia being present, it was something like maybe, 100 times or a big percentage times more soluble in the presence of this ligand than it was in the presence of just water. Any questions on? I think that wraps up this chapter. Any questions on this chapter or that information? Okay, give me 1 second here. Just want to rearrange a couple of things. Okay, then that will take us to, I believe, the next chapter, which I believe is, that was 16, so it's probably 17. That's sort of how math goes, I suppose, counting. So I think this is 17-ish. And that's when we got into thermodynamics in this chapter. And remember, thermodynamics here, we basically kind of built on some of the thermodynamic information that you perhaps learned in the previous class, and that was about delta H, which is our enthalpy. And our enthalpy, right, is our heat of a reaction. And basically, this helps us a lot of times determine whether or not a reaction is exothermic or endothermic. Exothermic meaning, obviously, heat and energy is released, and vice versa, energy is absorbed there in our endothermic process. The sort of manifestation of that in terms of values is it is negative for exothermic, and it is a positive value there for endothermic. So we started out talking about the idea about exothermic and reactions being spontaneous. And a reminder, as we talked about many times at this point, when we talk about reaction being spontaneous, again, it does not mean that the reaction occurs like super fast, right? Or, really quickly. It just means, it could occur fast, it could occur slow. But if we sort of determine if something is spontaneous, basically what we're saying is, under those conditions, we would expect this reaction to actually take place. The first sort of thermodynamic property we started talking about was delta S, which is the entropy. And the entropy is about really the randomness and disorder. And kind of a little bit different than sort of normally what we think about sort of in terms of the signs, like positive and negatives here. When we get a lot of order that's increasing, we actually start to get a decrease in the entropy, and we would expect the delta S here to become more negative. And vice versa, if we get an increase in the disorder, so a lot more disorder happening, we do see that the delta S increases, and in this case, that means that it does become more positive. So the more disorder, the more sort of disruption that we have there, we are increasing the entropy. It actually becomes more of a positive number. Also, in terms of units, a reminder that delta H is typically kilojoules and delta S is typically joules. So we always want to make sure we watch our units, especially since we have some formulas that involve both of these guys. The most common place where we can kind of see that disorder order sort of situation happening is as we transition from different states. So obviously the delta S there of solid is less than the delta S of liquid, and a lot less than the delta S of gas. Again, if you just think about sort of gas molecules flying around, there's a lot of disorder. We would expect a lot of entropy basically being there in that particular case. We talked about that entropy is related to probability, and we saw sometimes referred to as the Boltzmann equation, which is basically S is equal to K natural log of W. W is what is referred to as a microstate. It's basically the different ways that you could accomplish something. K is Boltzmann's constant. And roughly 1.38 times 10 to the minus 23 joules per Kelvin, in case that comes up in a Jeopardy question. But what we basically learned here was obviously the more ways you could sort of do something, the more probable that's going to occur, that event will occur, and the sort of higher the entropy there would be. If there's only sort of one way to sort of do something, you take the natural log of 1 is 0. That basically kind of zeroes out this equation. And we have a much lower entropy value that basically occurs. I think we talked about the idea that there's much more ways to screw things up, right, than to do things right. And, so that entropy value sort of increases. How do we use entropy to determine whether or not a reaction is going to be sort of spontaneous or not? We did need to calculate basically the delta S of the universe. And the delta S of the universe basically is made up of two things: delta S of the system, or the reaction, plus the delta S of the surroundings. And if we did get this value and it was sort of a positive number greater than 0, then we're looking at a spontaneous reaction occurring. Obviously, the opposite would be true. If it's less than 0, then it would be non-spontaneous. If it happened to be equal to 0, then it would be at equilibrium. Again, less than 0 would be non-spontaneous. Now, how do we calculate both of these things? So we talked about sort of how to go about calculating these guys. The delta S of the system is pretty much like most thermodynamic properties. You basically can look up these values in a table and take the delta S of the products minus your delta S of the reactants. And again, here, obviously, like normal, when we do these type of calculations, we would want to take any coefficients basically and multiply them by the values that we see in the table. So again, if you had an arrow where it was like 2 CO2, you would want to take the value of CO2 and multiply it by 2 as you're doing that. And that will give us our delta S of the system. Remember that we can make a fairly good prediction in terms of what the sign would be for a delta S of the system based on the reaction and kind of how many gas molecules you got on both sides, especially if gas molecules are involved. Remember that if you sort of go from a situation where you increase the gas molecules on the product side, we would expect the delta S to increase and become more sort of disorder happening there and a positive value, and vice versa. Obviously, if you go from a gas molecules to on the product side and they decrease in terms of the gas molecules, we're creating a lot more order, and we would expect that the delta S of the system would end up being negative. So again, as we talked about, even before you sort of did your calculation, you have a good idea, a good way to sort of figure out, does my calculation sort of make sense? Now, the surroundings, remember, is related to our delta H of the system. So the delta S of the surroundings is equal to minus, and this is the one that has the negative there, delta H of the system divided by the temperature that's in Kelvin, obviously. And in this case, remember that what we talked about is if the system is exothermic, is giving off the heat and energy to the surroundings, when that heat and energy is absorbed by the surroundings, it's going to cause a lot more disorder in everybody that's flying around in the surroundings. And we would expect that the delta S of the surroundings would sort of increase in that case. And that's why the negative is there, because if the delta H is negative and that negative, that turns our delta S of our surroundings into a positive number, which again would increase the amount of disorder in the surroundings. Vice versa, if it was endothermic, that means heat and energy is being removed basically from the surroundings to the system. That's going to cause the surroundings basically to kind of slow up and become more ordered. That positive delta H and that negative that's in the formula will turn our delta S of the surroundings to a negative number in that case, which also makes sense as we would be increasing the order in that situation. Remember, we saw an equation later where we rearranged sort of the formula that looks just like this, but does not have the negative in there. So again, that negative is important here for that relationship. We also talked about that the temperature of the surroundings does make a difference in terms of whether or not you see a big change occur. Um, Again, if the temperature of surroundings is very, very high to begin with, you might not see that big of a change in terms of the entropy of the surroundings because there's already a lot of energy in there to begin with. Remember that we don't use, again, both of these guys here to determine spontaneity. We kind of combo them together, calculate our delta S of the universe, and that, again, is what's going to kind of determine whether or not a reaction is going to be spontaneous. Any questions on delta S? Also, in this chapter, we moved on to some other letters in the alphabet there, and we got to G, which is good. And G, or delta G, there is our Gibbs free energy. And much like the name implies, it is basically energy available to do some type of work. We saw a number of sort of equations there that involve delta G. And as we sort of talked about, you might just want to kind of choose the one, that sort of fits the information that's given to you in the problem. We can use delta G, and if delta G is found to be negative, then the reaction is going to be spontaneous. If we calculate delta G and it's basically positive, I know it looks like a 6, but we'll go delta G. The reaction will be non-spontaneous the way it's written. And if delta G is equal to 0, then we are at equilibrium. Some of the equations that we talked about, calculating delta G, if you're just given the equation, nothing else, you could do delta G of the reaction, just like we did everything else here. Our delta G of our products minus our delta G of our reactants. Obviously, these would be table values. You would look them up and obviously adjust based on the coefficients and calculate those guys. If you happen to have the delta H or delta S, we can use this equation here. The delta G is equal to delta H minus T delta S. This is definitely one of many equations we've seen over the chapters here that we want to watch out in units. Again, this guy being kilojoules, this guy being joules. We also talked about that we can use this equation here for a couple of things. First off, we can use it to basically make a prediction based on the signs of delta H and delta S as to whether or not we expect the reaction to be spontaneous under sort of a low temperature, high temperature, normal temperature sort of situation. In addition, we could also use this equation if you remember that if we did calculate delta G and it was a non-spontaneous reaction, we could actually rearrange this equation by setting delta G equal to 0 and rearranging and solving for T, which would equal delta H divided by delta S. And we could use this rearrangement to figure out what is the minimum temperature to become spontaneous, that this reaction would become spontaneous. So it's come a wide variety of use of this sort of equation. We've used it for a number of different things. Again, allows you to kind of figure out those things as well. This is also the one, if you remember, we talked about phase changes. And again, phase changes, spell that there, also occur at equilibrium, which means pretty much our delta G here would also, again, equal 0. And rearrange this, we could solve for delta S, which is delta H divided by T. Again, this is the reaction or the formula that looks just like the surroundings formula, but we use this for something like delta S of vaporization, for example, where this would be the delta H of vaporization. And again, there is no built-in negative sign here. And again, that's the major difference there between sort of that one and the surroundings one that we saw. Again, this one is really based off of that equation there. We also saw that under certain conditions, maybe we're not under standard conditions. So remember that when we sort of talk about these sort of thermodynamic sort of properties and those type of things, when we talk about standard sort of table conditions, if you will, kind of standard conditions, we're talking about things where the temperature is 25 degrees Celsius. If we're dealing with pressure, just 1 atmosphere. If we're dealing with concentration, it's 1 molar. If we're not in that sort of situation, we can sort of calculate sort of the effect it would have on some of these thermodynamic properties. And I think maybe one of the first ones we saw in that aspect was the delta G one, where we have delta G is equal to delta G naught, and this is plus RT natural log of Q. This again being, if you want to think about it that way, sort of non-standard conditions is sort of standard conditions, basically your products minus your reactants from the table. R here obviously is our 8.314 gas guy. That guy is obviously our temperature in Kelvin. And Q is like a normal reaction quotient that we've talked about many times, which is our products over our reactants here. So we can use this to figure out, if we happen not to be under some type of standard conditions. Most often it's one of these two sort of situations, or, not 1 molar or 1 atmosphere. We could kind of see sort of the effect of delta G. We could see, under standard conditions, maybe it's non-spontaneous, but by playing with some of the concentrations, we could maybe turn a non-spontaneous reaction into a spontaneous reaction by kind of playing with those concentrations. When we do get to equilibrium, this formula here, basically our delta G would equal 0 and our Q would become K. And that equation right there then becomes delta G naught is equal to minus RT natural log of K. And again, this is the one with the negative in there. And again, sometimes people sort of miss that one along the way because of that rearranging. So this guy plus, this guy negative there. And I believe that wraps up the thermodynamics chapter there. Any questions on thermodynamics? Okay. Then we were off to, I'll go with 18, I think it is. And that was electrochemistry. So obviously this involved redox reactions, and obviously redox is oxidation and reduction. Oxidation has several definitions we talked about. The one we mostly deal with here in general chemistry is basically losing electrons. It also can be gaining oxygen. It also can be losing hydrogen. And again, if you take organic chemistry, those are kind of the ones you see a lot. Reduction is gaining electrons, and basically the opposite definitions there for oxygen and hydrogen, losing oxygen from reactants to products and gaining hydrogen as you go from reactants to products is sort of your basic sort of definition there of reduction. Again, like I said, most cases in sort of general chemistry, we oftentimes just kind of focus on those two guys. You do see a lot more of the others there in organic. Things being oxidized and things being reduced can basically be summed up, if you're not sure how to figure it out, by just following the charges. And we talked about just a basic number line can help you do that. When things lose electrons, they become more positive and head in this direction. So if you just follow the oxidation state and it's heading towards the right, it is becoming oxidized. And things that gain electrons become more negative. So if you just follow the oxidation state from reactants to products and you're heading to the left there, it becomes more negative and going through reduction. These guys should not be confused, right, with our reducing agents and our oxidizing agents. Remember that these guys essentially are the opposite of their names. So the reducing agent is the substance that gets oxidized. While the oxidizing agent is the substance that gets reduced. And again, the reason for that is that they cause basically that effect in the other compound. So in order for something to get oxidized, it has to cause somebody to I'm sorry, in order for something to get oxidized, when it loses electrons, something else will gain those electrons and become reduced. And when somebody gets reduced, in order for them to gain those electrons, somebody else has to lose the electrons and they become oxidized. How do we do that? We basically follow the oxidation state, our number, sometimes referred to. And basically, that's the charge that those elements would have if there was a complete transfer of electrons. So that was the charge that those elements would have if there was a complete transfer of electrons. Remember that we oftentimes think about sort of charges of elements based on ionic compounds. And when you're dealing with an ionic compound, a metal and a non-metal, what's always going to happen because of the properties of metals and non-metals is the metals pretty much will lay up the electrons to give them away. Non-metals will pick them up and always gain them. And because of that situation, if we're trying to assign oxidation numbers for an ionic compound, they really do end up being the same as the charges we're normally associated with them. But when we get those elements in things that are really bonded together, sort of covalently, sharing electrons and stuff like that, there are certain elements that may take on a more positive, for example, oxidation number than the negative one we sort of associate with it. For example, chlorine, we can have chlorine, and we normally think about chlorine a lot of times like, hey, so let's try that again. Hey, sodium chloride, this guy's +1, -1. But when we get, chlorine involved in like ClO4 minus, in this arrangement, this is really chlorine sharing electrons with oxygen. So we don't really have a complete transfer of electrons like we do here in this ionic compound. So it takes on a different type of sort of charge, if you will, or oxidation number. So oxygen, as we talked about, always a good place to start. It's always -2. That gives you -8 overall here. It has a -1 charge, which means in this case, instead of that normal -1 sort of orientation we think about chlorine, it's actually sort of taking on a +7 sort of persona here in this arrangement where it's sharing electrons. So again, oxidation number is not always sort of what we have in our head in terms of the charges of certain elements. And again, it's really, the basis of the difference between sort of how they are in those molecules. Again, in ionic situation, we have a complete transfer of electrons in a more covalent sharing of electrons. So we get these sort of picking up more of a partial positive charges and have a more positive sort of aspect in this case, in the case of chlorine. We also talked about that basically the oxidation number of anybody in their standard state is 0. Again, oxygen, a good place to start with. Always -2, except if it is peroxide, it is -1 in that particular case. And by the way, you can, as we also talked about, have oxidation states that are not whole numbers, so that is possible as well. We sort of finished up the beginning part of this chapter reviewing and just make sure everybody's on the same page in terms of balancing redox reactions. And when we balance basic redox reactions, there's always sort of a oxidation half reaction, and there's always a reduction half reaction. And the way we know that is by the position of the electrons. In an oxidation half reaction, it's on the product side. In a reduction half reaction, it's on the reactant side. And when we want to basically add those together, we always want to make sure that they are the same number because there's really a conservative transfer of electrons. Pretty much whatever that's getting oxidized, however many electrons that guy loses, is pretty much the exact same amount of electrons that the guy accepts on the reduction side of the reaction. So we may need to multiply one of the half reactions by coefficients. I may need to multiply, both half reactions by a common number there. But the goal is to always make sure that the electrons completely sort of cancel out. And that's sort of like kind of a neutral solution, if you will, basic sort of redox reaction. When we're dealing with acidic are basic solutions in terms of balancing redox reactions. These are the cases where we basically use water to balance oxygen. And then obviously, whichever side we add the water to, we're also adding 2 hydrogens. So the opposite side should always get sort of the 2 hydrogens for every water that you add, or H pluses, so that you're not short along the way. Remember, we kind of do balance everything other than oxygen and hydrogen. Then we balance oxygen by adding water. Then we add electrons, make sure we have the same number of electrons in each half reaction, add them back together. At that point, if you did everything correctly, you should be balanced in acidic solution. At that point, once you've balanced it in acidic solution, and if you really were interested in basic solution, to turn it to basic, you would have obviously in your reaction a certain number of H pluses on one side or the other, for example. And basically we add the same amount of hydroxide to both sides. So again, not just one side here, but actually both sides. And what usually will happen is these guys will come together to form water. And in most cases, you'll probably have like a water on the other side that maybe could do some canceling down, and sort of end up with, hydroxide here. And by the way, that is how you know you're balanced in the acidic or basic conditions. When we look at the balanced equation here, we see H plus, which tells us we are balanced in acidic conditions. And when we look at our equation, once we balance it in basic conditions, you should have just OH minus involved. And again, that will tell us that we are balanced in basic conditions in this case. Remember, to be properly balanced, the equation does need to be balanced basically in sort of 2 ways, if you will. It needs to be balanced first off like a normal equation. You need to have the same number of elements on both sides. Then you also need to have, when you look at the arrow, the same charge, overall charge on both sides. Remember that the overall charge on both sides does not mean that it has to, excuse me, does not mean that it has to be 0 on both sides, but it does just need to be basically the exact same number on both sides. So +2 overall on both sides, positive, 3 on both sides, -2 on both sides, but it does need to be pretty much the same overall number on both sides. Then you properly balance those equations. Any questions on sort of the intro redox stuff? Then we got into, in this chapter, sort of the basic part of what this chapter was about, and that was really sort of galvanic cells. And we started talking about galvanic cells here. And a galvanic cell, come here, right, there you go. Galvanic cell basically has several parts. So if you remember, if we just kind of sketch it really quickly, maybe really badly, but we'll try our best here. We basically have, sort of an electrode that's kind of hooked up through a wire, goes through the voltage meter down to the other side. And we also have something kind of connecting both of these guys. So it sort of looks like this. And, it doesn't always have to be on the left-hand side, but a lot of times it is drawn like that. We have sort of our anode side in our galvanic cell, and that's really where oxidation occurs. And basically what's happening is we have a solution that has the same ion. So we say that was zinc solid up there. In the solution, we would have some zinc ions floating around. We would also have some negative spectator ion floating around as well. But when it loses electrons, basically what's going to happen is that solid zinc will then go for a swim down into basically the solution. Those electrons that are lost will travel along the wire, create some voltage, come down to the other side where we have another solid electrode, for example. We'll just call it copper for the sake of this purpose. And in this solution, we would obviously have some copper ions floating around, where those electrons would then combine with the copper ions that are floating around and go through reduction, which is on our cathode side here. And basically what's going to happen in that case is the ions are going to jump out of solution, if you want to think about it, and kind of go into the solid phase. So we have this reaction that's happening here, this sort of oxidation reduction reaction that's occurring. Um, and we also have another important part here that connects them, which is our salt bridge. And remember that basically our salt bridge is some type of ionic compound, so a positive and a negative guy there, like say potassium chloride or something of that nature. And what's going to happen is in this particular case, as we kind of do this reaction will take place. We're going to kind of get a buildup of, sort of the wrong charge is going to happen. We're going to get a buildup of a lot of negative charge over here on the right-hand side because all those positive guys are coming out of solution, leaving our negative spectator ion there, building up negative charge. Over here, we're getting a buildup of positive charge coming in on the anode side. And the salt bridge is really there to sort of balance that out, sort of that buildup of the charge that we don't really want to sort of occur. And we get our sort of ions floating both ways to keep the overall charges sort of where they need to be. There is sort of a potential difference, right? EMF, a cell voltage, if you will, this sort of potential difference between the two that really sort of drives those electrons going from the anode to the cathode. We can write the overall reaction that's taking place, so in this particular case here, on our anode side, we would have our zinc, and on this side, we would have our copper, and it would be going to our zinc. Zinc with a 2 plus, and that was aqueous. And our solid copper in this case. And remember that, we could get our balanced equation here. We could also write what is referred to as the cell diagram. Cell diagram is sort of a shorthand of the reaction where we would write something like zinc. And in the first part is pretty much our anode compartment separated by the salt bridge going to our sort of cathode compartment over here. Again, sometimes they'll include things like the molarity of it. If you happen to have a pressure, it would include the pressure and so forth. So that's, again, a sort of a shorthand. Also remember that sort of the basic setup of most of these sort of cell diagrams is sort of reactant, product, as you can see here, reactant, product. So that's sort of how it's set up and how you could go, again, from a cell diagram to the actual reaction by following that sort of method. They basically made the hydrogen electrode sort of the standard, and sometimes referred to as the She, which is the standard hydrogen electrode, gave it a value of basically 0 volts. And remember, they used this basically to hook up and make cells, and they used it to figure out what are sometimes referred to as SRP values. SRP values are standard reduction potential values. And much like the name implies, when you look it up in this table, you pretty much will have all reduction reactions, which means electrons are basically on the reactant side. Because these are oxidation and reduction reactions, that means, technically speaking, when we grab one of these guys out of the table, it is really written incorrectly. So if we do reverse it, so for example, if this E value was positive 0.8 volts, and we reversed that reaction and made it into an oxidation reaction, remember, we do change the sign of it by reversing that reaction. Also remember, in the lack of any other information given to you, when you look at that table, if you're not given the reaction or anything else, other information, the one that is more positive in terms of the SRP value will typically be your cathode, and by default, your other guy would be your anode. Also very important, as we saw in a number of examples, that if they do give you the overall reaction or tell you how the reaction is going, you do need to follow basically what it says there, what is being oxidized, what is being reduced, to help you determine, which one is your anode or cathode. We could calculate E of the cell. We also talked about a couple different ways to do this, but we'll just roll here with the cathode minus the anode. And remember that when we use this equation, the purpose of the subtraction here is to actually do this part of it for you, change the sign. So as we talked about a number of times, if you choose to not change the sign that you find in the table, you should do the subtraction, because that subtraction will change the sign correctly for you. If you want to change the sign yourself, as we talked about, so if you decide you want to change the sign of the anode that you find in the table, then you should definitely not subtract, but you then should add. So again, that was the two different things there, the adding or subtraction. They both obviously should get you the correct answer. You just don't want to do a combination of both of those where you change the sign and then subtract, because you might actually undo what you want there. A positive cell voltage is good. It means usually it's a spontaneous reaction. Remember, a positive cell voltage is sort of a good one. It's usually a spontaneous reaction. It's a spontaneous reaction because of, for example, the delta G is equal to minus NF of E. And again, if this guy is positive, F being Faraday's constant, N being the moles, positive, and the negative here will turn our delta G into a negative, and it would be a spontaneous reaction. Opposite would be true if our E was negative. The negative and negative there would turn our delta G into a positive number, which would be non-spontaneous. So typically when we see that positive E relates to usually a negative delta G, and that usually means a spontaneous heading from reactants to products. We also saw a couple of equations where we can do some calculations here involving also the equilibrium constant. We could do our E of our cell is equal to RT-NF natural log of K. We also saw a couple of versions of this equation where at 25 degrees Celsius, it reduces down to like 0.0257 volts or 0.0592 volts over N. Again, like we talked about, you don't necessarily have to remember those equations because you could just put all the numbers into here, even if it is involving 25 degrees Celsius. This is again the relationship between our E and our K, and much like our G and our E relationship, we would expect all those guys really to sort of fit together nicely, and we do typically see that again thinking about E, G, and K. Again, if we have positive value here, we expect our G to be negative, which means the reaction is spontaneous. If the reaction is spontaneous, we should expect products to be favored. Products being favored means we have probably more products than reactants at equilibrium, and we should have a sort of K that's greater than 1, right? Or sort of a large value of K. Vice versa, if we have a negative E, we should expect what we just talked about, a positive delta G. Positive delta G would imply non-spontaneous. Reactants are favored. If reactants are favored, we would have more reactants than products, which means when we take products divided by reactants, we will actually get a small value of K. So these are ways that you could kind of tie these things together and again, make sure that, your answers do make sense when you do some of these calculations along the way. Any questions on that so far there? And in addition to sort of our K and all that, we also saw here in this chapter basically a situation where maybe we're not, again, under standard conditions. So we're not sort of at standard conditions. And that brought us our Nernst equation. And our Nernst equation was E is equal to E naught minus RT NF natural log of Q. We saw sort of the same couple of other formulas that have those kind of 0.025 number and 0.0592 number in there. But same idea as what we saw with the delta G. Again, you can kind of think of that as non-standard conditions. This is standard conditions of E of the cathode minus E of the anode. These are our normal sort of characters here, our 8.314, our temperature, our Faraday's constant, 96,500, and again, our Q, which is our products, right, divided by our reactants. Again, much like the one we talked about with Q here, we may have under sort of standard conditions a cell that basically is going to be non-spontaneous. Maybe it has a negative E value, but playing with concentrations, maybe even playing with temperature and those type of things, you may be able to turn a non-spontaneous reaction into a spontaneous reaction by doing that. And a reminder that essentially how we go from the Nernst equation really to this equation is that same sort of relationship that at equilibrium, our E will equal 0 and our Q will equal K. And again, that's sort of how we get from there to there, and that's how we get to that equation. So that Nernst equation, whenever you sort of got a galvanic cell happening and you got some different concentrations given to you and stuff like that that are not 1 molar, you should probably always think about using that Nernst equation. We finished up this chapter talking about electrolysis. And electrolysis is basically making a non-spontaneous reaction sort of to occur there by applying a electrical current, for example. So again, normally water doesn't break apart into sort of its elements of hydrogen and oxygen gas, not balanced, obviously. But if we run an electrical current through it, we basically can sort of break it apart. Electrolysis of water, we take some sodium chloride, and we sort of run an electrical current from it. We could kind of get some sodium back, and we get some chlorine gas, which obviously doesn't normally happen as well. I guess we should do the right thing and put some balancing in there, right? So we need there like a 2 and a 2 perhaps. But a reminder that when we're doing this, we're sort of reversing the reaction in a sense. So sometimes people do get the anode and cathode reactions sort of backwards. So you got to remember, for example, if we are dealing with sodium chloride, we're really dealing with Na plus, and Cl minus is sort of our starting guys, and we're ending with we're basically ending with 2 of the sodium liquids or solids, and we're ending with chlorine gas. So in the case of sodium, we're actually going from +1 to 0, which means it's actually going through reduction here. And that means that would technically be our cathode in this case. The chloride is going from -1 to 0, and that is going through oxidation. So again, sometimes people have trouble with that, sort of opposite of what we think about when we kind of do the reverse of that reaction. When we put these guys going to here, again, he's going from 0 to +1 being oxidized, and going from 0 to -1 being reduced. But in this case, we're actually starting with our product. So we're kind of running it in this direction, hence making that sort of non-spontaneous process occurring. And thus, our anode and cathode are sort of, I don't want to say backwards, but different than maybe what we normally sort of think about. We talked about sort of calculations involving electrolysis, and it's fairly kind of straightforward the way it is. We usually are given the charge in the current and amperage. So we're usually given the amperage, and an amperage is equal to a coulomb over a second. And they oftentimes will tell us, how long we ran the cell. How many hours, maybe minutes, whatever it may be. We typically want to take the time that we ran the cell, and we want to get it into units of seconds. And that's so that we can basically take our amperage times our seconds, which is our time. Basically our amps times our time here. That gives us our coulomb of charge. That's where we use Faraday's constant to convert it into moles of electrons. And at this point, that's where those half reactions are going to really sort of come into play. And from your balanced half reaction, you could get kind of like a mole of electrons to a, say, mole of like a metal, for example, or moles of electrons to a mole of a non-metal. And you could use that to basically go from moles of electrons to, say, moles of sodium in the previous example, or moles of electrons to moles of chlorine in the previous example. And there's usually kind of two things that we sometimes try to calculate here, is basically how many grams of, say, a metal may be produced. So at that point, you would have the moles, for example, of a metal. You could use the molar mass from the periodic table to figure out how many grams of metal would be made. Remember, also, this is where we saw that, we sometimes may collect a gas. And in a gas situation, we may use PV equals nRT and solve for the volume here to figure out, what volume of the gas was collected by basically using the moles. Obviously, the temperature and the pressure would be provided to you in this particular case. Any questions on that there? That, I believe, wraps up that chapter. Now, rolling into the next chapter, which is, we'll go with 19, and that is when we started talking about some nuclear chemistry. And nuclear chemistry obviously involves nuclear reactions there. And we saw some different sort of particles along the way here. We had our alpha, our beta, our gamma. We also had some positrons. We had protons, obviously, and neutrons. So unlike sort of regular chemistry, I guess so, sort of inorganic chemistry and not nuclear chemistry, in regular sort of chemical reactions, pretty much everything deals with electrons. Electrons either being transferred, being shared, those type of things. But different in sort of nuclear chemistry here, we deal with basically what's going on in the nucleus. So we deal with, protons and neutrons and these guys getting sort of converted from one thing to the next sometimes. And some of these particles are important. We also saw some sort of symbols that are commonly used. So for a proton, these guys are commonly used. A neutron, an electron, or a beta particle are sometimes sort of used like that. We also have a positron. We also have positron can also be used with the beta symbol as well. Remember, helium basically represents the alpha particle, right? And when we look at these guys, the top numbers, right, when we do that is the mass number. Bottom number there is the atomic number. And remember that the mass number is the number of protons plus the number of neutrons. The atomic number is just the number of protons. You could use those two and subtract them, and that will usually give you the number of neutrons that are sort of present in here. The mass number, atomic number, is really important, and a reminder that it is only the atomic number there that you could find on the periodic table. That is obviously the number that you see above the symbol. Remember that the mass number is not the number that you see on the bottom of the symbol on the periodic table. That is actually the atomic mass. So that is actually something a little bit different than that. So remember that when you calculate the mass number, atomic number, or you state how many protons, electrons, neutrons there are, those are all positive whole numbers they should be. So they should always be positive whole numbers. They also play an important role in terms of balancing nuclear equations. So unlike chemical reactions, nuclear reactions, there really is no conservation of the elements. So in a sort of chemical reaction, if we started with 4 carbons, we should end with 4 carbons. But in a nuclear reaction, we don't do that. We actually make new elements because we are changing protons, right? Protons are really what determines what element you're dealing with. So as we change the number of protons, we are going from, say, one element to the next. But when we balance sort of a nuclear equation, it's not terribly bad. Basically, what you want to do is take all the mass numbers that you got on the left-hand side. They need to equal all of the mass numbers that you have on the right-hand side, and vice versa here as well. All the atomic numbers that you have on the left-hand side need to equal all the atomic numbers that you have basically on the right-hand side. So remember, in these sort of situations, a couple of things can occur. You probably maybe have an equation, something is missing. And if something is missing, usually you want to find the missing atomic number, go to the periodic table. That usually will tell you what element's missing. Could also be a particle, but it'll give you that sort of information. And then obviously you could add up your mass number. The other couple of things we talked about are some words that you commonly see in nuclear chemistry. Emission, or decay through a certain process. Those basically mean that those particles will end up on the product side. If you have something like an electron capture, or something is bombarded with a certain neutron or something like that, that means that those particles will end up on the reactant side of the equation. So, those are a couple of things that we do that. So if it says, hey, this guy went through beta decay, write the reaction. Again, when you would write the reaction, whatever you're starting with would be here. You would then obviously put your beta particle over here and try to find what the missing element is by going with the atomic number, mass number, and then obviously symbol that you could get from the periodic table. Any questions on that there? We talked about also stability, and sort of a couple of ways you can look at stability. And one sort of big way that we looked at stability was referred to as the N to Z ratio. That's the neutron basically to proton, right? A sort of ratio that's happening there. And there is this sort of thing, we saw a graph, and it's again sometimes called certain things, but sometimes it's the belt of stability. It's the valley of stability as well, if you like that one better. But there is a certain ratio of neutrons to protons which are sort of acceptable for different elements, and it is based on atomic number. So if your atomic number is like 1 to 20, a ratio of 1 is acceptable and stable. If you're kind of 20 to 40, the ratio then goes up a little bit to 1.25. If your atomic number is like 40 to 80, then the ratio is something like 1.5. And again, we use these as sort of hard cutoffs. As you can see, there is some gray areas between them where one stops and the other starts. So, in reality, some people will say it's okay, depending on, so where it's at. But for us in this class, just to make it a little bit easier, we go with the straight. It either is that number or is too high or too low. So there's no sort of gray areas happening here, even though in real life there is gray areas. And if we do calculate those ratios and it is too high, basically it will go through a beta decay to try to bring it back down closer to that value of stability. As we talked about, it may not hit it after one beta decay. It may take more, but we usually just do the one beta decay because it then should move you towards the right direction. If it's too low here, we can do one of two things, either a positron emission or an electron capture, and to some extent an alpha decay, but it's not as efficient. And basically what's happening in these situations is we're converting things. So for example, perhaps we're taking some neutrons to protons here, we're taking some protons to neutrons here, and again that should kind of bring you back up closer to that sort of stability sort of range. questions on that so far? All right, so we're out of time here on lecture. So we will continue in lab at 1, finish up the last couple of chapters. Again, we'll talk about the final exam